Okay, hello again. So this video, we will talk about the scattering cross-section. Now, this stuff is going to take a while because there's a lot of ideas and mathematics. Again, I'm going to skip some of the mathematics. My point is to get as much of it as I can, but not dive into a big derivation that distracts from the main idea. So let's switch here. First thing I want to just do is do a quick review of what I've talked about so far. First of all, we have to remember we're trying to determine the wave function of this electron that is scattered by a central or spherical potential. Now, this potential is going to be a model for the interaction between the scattered electron and the atom or the molecule, and it'll be something that we have to calculate in the future as well. But if we know the potential function V of r, we can write the Schrodinger equation in spherical coordinates, which we've done before. We end up with an angular momentum operator squared, which is really due again to the centrifugal force that the electron can experience as it kind of goes around the atom. When we plug in our kind of expansion of the wave function in terms of these spherical harmonics, we end up with the radial equations describing the radial function that we have to solve for u of L, or u sub L of r. Now I should point out I did make a mistake in the last two videos. There should be a minus sign here, and I apologize again for that. I'm going to make probably mistakes like that. Also, the writing, I hope you can understand. I'm doing this fairly quickly. I could spend a lot of time typing this all up, but for right now, we're just going to try to do it by hand. So the last video, we showed that we can write the asymptotic solution, which is in the space where the potential basically is zero, far enough away from the atom, in terms of Riccati-Bessel and Riccati-Neumann functions. And a scattering or a matrix KL, a matrix element, which is related to a phase shift for each partial wave. Now, by partial wave, I mean each L component here. Now, there, again, is an M that I have in here. In a future video, we'll see that for a spherical potential, the M does not matter. It kind of goes away because for our spherical potential, everything really only depends on r and theta. It does not depend on phi. And M describes the phi dependence, the azimuthal dependence of the function. Okay, but let's get into what we call the differential cross-section. So when you do an experiment, when an experimentalist does an experiment, often what they do is they will set up a beam of incident particles. Incident electrons, incident positrons, incident positronium particles, right? And they create this beam, and then it hits a target. Now, typically speaking, right, what you'll have is maybe a gas of atoms. So there are a lot of atoms in there, but you have to set it up so that the assumption is that each electron that comes in, the beam is kind of sparse enough, and the gas is not too dense so that each electron scatters only once from each atom. If you get it too dense, things change, and we have to define things a little differently. But in this situation where you have basically one electron scattering from one atom, what we can count are the number of incident particles coming in with a speed v or a initial kinetic energy, and then the number that scatter into a certain angle here. So what you'll do is you'll put your detector over here, and it will count the number of particles coming in per second, right? Basically the current of particles entering the detector. Now the detector, we say subtends a certain solid angle, a d omega, which is the differential angle sine theta d theta d phi. It's kind of the part of the whole sphere. In fact, again, if you integrate this over all the angles, you'll get this equal to 4 pi. And so often for this solid angle, people talk about the unit of steradians, which is kind of a generalization of the radian from just a circle to a sphere. In any case, what we talk about then is our incident flux of particles. And I talked about this a little bit when we talked about the one-dimensional problem. You have a number of incident particles per volume, or a density, number density, times the speed v of the particles. So this can describe your incident beam, number of particles per volume times the speed, which is the incident flux. Now, it should turn out that your scattered current, the number of particles scattered per second, I really should put time because it doesn't have to be in seconds, right? You could use a different unit to measure the time. But the number of particles scattered per time, per second, should be proportional to the incident flux, right? The bigger the flux is, the more particles coming in per second, the more scattered you should get per second. It also should be proportional to the size of this angle, the size of the detector. If you make the detector big, you'll get a proportionate more number of particles being scattered. The proportionality function or constant is what we call the differential scattering cross-section, or just differential cross-section. So basically what is done in an experiment is you set up your beam and you measure the incident flux, right? You set it up, you measure how many particles are coming in per second, and then you divide that in, well, you measure the scattered current, and then you divide the two, and that gives you this cross section. Now the division takes care of, relative number of particles, right? If you increase the incoming particles, the outgoing particles increases, and you get a measured property that kind of tells you everything you need to know about the interaction that went on to scatter those particles. Now, one other thing I should point out, I am talking about what's called an elastic cross-section right now. And that, what I mean is that there's no exchange of energy. The energy of the incident particles is equal to the energy going out. Now the momentum has changed because the direction has changed, but the energy has not. And as we will recall, this will mean that our K, right, our K that appears in our sign of KR or e to the IKR does not change. Okay, let's go on here now. With all of these new ideas, it can be kind of complicated. But one thing I want to point out, why is it called a cross-section? Well, for one reason, it's related to an effective area. If you look at the units here, well, I've got for my outgoing current, my scattered current, I have a number per second. For my incident flux, it's a number per meter squared per second, right? It's a velocity, which is meters per second over a volume. So one of the meters cancels. And then I get an angle, a solid angle in steradians. So canceling stuff out, I find that the units of my differential cross-section are meters squared per steradian. So it's an area per steradian per angle, per, I guess, what you call solid angle. So another notation that's used for differential cross-section is d sigma d omega. It's going to be a little confusing, but what I mean, it's the part of the area of the target that scatters an incident particle into this particular solid angle. So I could also define a total cross-section, right? Now, by a total cross-section, I mean the total number of particles that are scattered divided by the incident flux. So the way to get the total cross-section is to take my differential cross-section and integrate it over all angles, right? So if I use my d sigma d omega notation, you get this. It's kind of a little bit confusing because I'm really going to take my differential cross-section and integrate it over all the angles, but I don't cancel those d omegas out. So again, remembering that the solid angle is sine theta d theta d phi, I have to do an integral over all these angles. It's really a double integral. Integral over sine of theta goes from pi, 180 to negative pi, or actually negative pi to pi, right? It goes over the whole polar angle range. Integral over phi goes from 0 to 2 pi. Now, since this doesn't depend on phi, which is the case for a purely spherically symmetric interaction, I could write this as 2 pi. Integral over my azimuthal angle, d phi, is just 2 pi. Integral negative pi pi. Sigma, this should be sigma of theta, my differential cross-section, sine theta d theta. Last thing here, just a little mathematical thing. If I make a change of variables, I can write this integral as negative 1 to 1 of sigma of x dx. Right now, by that I mean sine of theta d theta. I basically change variables, whoops, to sine of theta, and so this means that my differential cross-section will probably depend on sine of theta in some way. So I really should put x is equal to sine of theta. Now this only works, again, if your cross-section is a function of sine of theta or cosine of theta. Okay, maybe I went too far a little bit there, but we can see that later. My main point is that my total cross-section is the integral over all angles of the differential cross-section. Now, what we want to do is look at the wave function and try to figure out how to calculate this differential cross-section in terms of the waves. Now, again, I'm kind of going to skip over some stuff here, but how do we describe our incident beam? Okay, we just can describe it as an incoming plane wave. Now, when we talked about one dimension, we talked about e to the ikx. Now, what I really should write is not e to the ikr, but e to the ikz, right? So if I describe my z-axis as the axis along which the incident beam comes, I have e to the ikz instead of e to the ikx. Now that incident plane wave will scatter, and you'll get an outgoing sort of spherical wave that goes as you get to large R as e to the ikr over r. Now again, I'm not going to sit down and work through all the mathematical details, so you might have to take my word on it that this is an outgoing spherical wave, but you can show it from the solution to the Schrodinger equation if you plug it in. So asymptotically, I have, again, it's not e to the ikr, but e to the ikz here. My wave function that I'm trying to determine, basically, through all of this stuff, psi of r theta and phi goes as r gets big. It looks like an incoming plane wave and an outgoing spherical wave, right? So if you were to put your detector over here, you'd kind of have a plane wave that wasn't scattered and a scattered spherical wave. Your detector would kind of count the particles that come in based on the amplitude of the wave at each point. Now, I could put constants in here, but that just makes things a little more complicated. It turns out to work the same. But the constant that I have is this f of theta, right? It's a function of the angle theta. So my theta, again, is measured from the z-axis. And things don't depend on phi, which rotates around the z-axis here in the spherically symmetric case. It can if things are not spherically symmetric. Okay, but this coefficient of my outgoing wave is called the scattering amplitude. And it is what will be related to the differential and total cross sections. So how do we get that relation between cross section and scattering amplitude? Let's go back to our definition here. in terms of our scattered current that we're measuring and our incident flux that we create. We can note that our scattered flux, right? So we have a flux, which is a number per area per second, can be written as the number scattered per second divided by the area of the detector. Now this is going to be r squared times whatever the solid angle is of that detector, right? Again, right, if this was a whole sphere, it would be 4 pi, and 4 pi r squared would be our whole area of our sphere. But it's just that little solid angle of the detector. So I take my incident flux, divide it, and define it as the number scattered per second, which is what I really measure, right, in my detector. Divide it by the area of the detector, basically. So it's a current over area. So then I'm going to use this and write that my scattered flux times r squared d omega is equal to n scattered per second, right? It's equal to my current. And that's equal to my differential cross section times my incident flux times my angle of my detector, basically my solid angle. When I plug these in, what I find is that my differential cross section is equal to my scattered flux times r squared over my incident flux. It makes sense that the flux gets a little bit bigger as you get further away. It actually gets smaller because the scattered flux gets smaller. You have fewer particles in there. But you get this r squared because you're spreading out over a sphere. Now, we have to calculate those incident and scattered fluxes. How do we do that? Well, if you go back and look at the one-dimensional problem where the particle is just reflected from a barrier, I defined how you calculate flux. I'm not going to go through the details of it, but recall that for just a plain wave, right, a wave coming in along one direction, the z-axis in this case, not the x, the incident flux is h bar k over m. It's just the velocity. Now this would describe, in fact, a particle with 1 particle per second with a speed v. But again, right, it's all relative. If we increase the number of incident particles from 1 to 2 or 3, the scattered particles go up proportionally. And what we're just trying to find is that proportionality constant, sigma of theta. It can also be shown, and again, I wrote down previously how you calculate the flux, but I'm not going to show it here, but you can show that the flux of the scattered wave, which comes from that e to the ikr over r part, is given by this, h bar k over m, velocity over r squared. So you can see, right, the scattered flux does actually decrease as 1 over r squared, times the square of that constant. This always appears, right? We always give the square of our sort of normalization constant or our scattered amplitude. This is our scattering amplitude squared. So if we go back and divide from 15, we've got our things here. Divide our scattered flux by our incident flux and multiply by r squared. We find out, pretty simple thing, that our differential cross section is our scattering amplitude squared. Again, different notation, d sigma d omega, differential cross section equals f of theta squared. From that, we could integrate over all of our angles and get our total cross section, right? Just plug in that our differential cross section is our scattering amplitude squared. All right, a lot of work, a lot of new concepts. The next thing is, how do we calculate the scattering amplitude, right? That is going to come from solving, well, yeah, solving the radial equation. It's going to come from our matching. It's going to come from our phase shifts. So at that point, when we actually solve the radial equations, we'll get the phase shifts. The phase shifts will be related to our scattering amplitude. And then we will actually be able to calculate something that we can compare to a measurement. Now, at that point, it becomes hard a lot of times. There are very few problems you can actually solve by hand. most of them you got to do numerically. But I'm going to stop there. That's a lot of concepts for these last two videos. Hopefully you have a lot of questions. Let me know if you have questions about this, and maybe I can answer them in future videos or in person.